Everyone knows the scientists behind the atomic bomb, but almost nobody knows about the extraordinary machines that made it physically possible. Without them, the bomb would have remained a theory on a chalkboard. These machines had to exploit a mass difference of less than 1% between two uranium atoms, and they were housed inside buildings stretching 44 acres under a single roof, run day and night by thousands of young women who were never told what they were building. These are the forgotten machines of the Manhattan Project, and the real question is how any of them worked at all. The challenge facing the Manhattan Project was not simply one of scientific discovery, but of physical transformation, turning a handful of unstable atoms into kilograms of bomb material. At the heart of the problem was uranium, an element with two nearly identical forms, uranium-235 and uranium-238. The difference in their masses is just 0.36%, a gap so slight that no chemical process could separate them. Chemists, after years of effort, found themselves defeated by the stubborn laws of nature. The only hope lay in the world of machines, devices that could exploit the faint difference in mass at an atomic scale, over and over, until enough pure uranium-235 could be gathered for a weapon. The demand was staggering. The bomb would require kilograms of uranium-235, millions of trillions of atoms sifted one from another. In 1942, no industrial method for this separation existed anywhere in the world. Theoretical physics offered the principles, but the numbers were brutal. For every 1,000 atoms of uranium, only 7 were uranium-235. The rest were the heavier, inert uranium-238. To reach a single kilogram of usable material meant processing tons of ore, refining it into uranium hexafluoride gas, and then separating out the rare isotope with a precision that bordered on the impossible. Laboratory scale demonstrations had shown that electromagnetic fields or porous barriers could, in theory, nudge the lighter atoms away from the heavy ones. But these experiments yielded milligrams at best, barely enough to see, much less to build a bomb. The war demanded a leap from tabletop apparatus to factories the size of small cities. Engineers were tasked with designing machines that would run continuously, day and night, handling corrosive chemicals, extreme voltages, and delicate tolerances never before attempted at scale. No single approach could be trusted to work in time. Leaders in Washington and at Los Alamos insisted that every plausible method be pursued in parallel electromagnetic separation, gaseous diffusion, thermal diffusion, and in a separate branch, the production of plutonium in nuclear reactors. Each route required its own set of machines, its own infrastructure, and its own workforce, none of whom could be told exactly what they were building or why. The only certainty was the urgency of the mission, and the knowledge that failure would leave the bomb as nothing more than an idea on paper. The answer, if there was one, would come from machines built at a scale and speed the world had never seen. In March 1943, Oak Ridge's Building 9731 saw its lone Calutron prototype multiply into rows of machines, each one a mass spectrometer scaled for war. The heart of every Calutron was a 184-inch magnet, so massive it dwarfed most locomotives, built by Alice Chalmers and cooled by a dedicated water system that cycled millions of gallons daily. Inside these hulking magnets, uranium ions raced through vacuum tanks, their paths bent by magnetic fields with such precision that a fraction of a millimeter determined whether an atom became bomb fuel or waste. Lighter uranium, 235 ions, curved just enough to hit the collector plate. Heavier uranium, 238 ions, veered away. Scaling up this process brought new problems. As more ions crowded the beam, their own electric fields scattered the stream, blurring the separation and cutting yields. Engineers scrambled for solutions, using wider extraction slits, magnetic lens electrodes, and in the beta tracks, a low-pressure helium fill to tame the space charge. Adjustments were made overnight, logged, and tested again as the clock pressed on. The machines demanded constant attention. Tennessee Eastman Corporation hired thousands of young women, many just out of high school, to operate the calutrons. Known as calutron girls, they learned to watch dials, tweak currents, and keep meticulous logs, all under strict secrecy. One operator recalled that they were told it was something to help win the war, but nothing more. Shifts ran 10 hours, day and night. The rule was simple. What you see, what you hear, what you do, let it stay here. In the control rooms, operators watched for the smallest sign of trouble, a flickering meter, a sudden temperature spike, or a cracked coolant hose. Any misstep could mean hours lost or a full shutdown. The work was repetitive, exacting, and exhausting. Yet by late 1943, the plant's daily output soared from a few grams to nearly 100 grams of uranium-235, enough to supply most of the uranium for the Hiroshima bomb. At its peak, more than 45,000 people worked at Y-12, half of them women. The true purpose of their labor remained hidden, even as the machines they tended became the pulse of the bomb's creation. K-25 stood as a mile-long wager on a process no one had ever mastered. Gaseous diffusion for uranium enrichment was unproven, and the scale was staggering. A 44-acre roof sheltering a U-shaped building that seemed to stretch without end. Inside, thousands of stages formed a continuous cascade, each coaxing uranium hexafluoride through a barrier so fine it made silk seem rough. The gas itself was a constant threat, corroding nearly anything it touched, especially when exposed to even a hint of moisture. Early designs called for solid nickel barriers, but the math was impossible. The entire nation's nickel supply would vanish before the first section was finished. Chrysler's engineering team, more familiar with chrome bumpers than atomic secrets, tackled the problem head-on. In Detroit, they transformed their Lynch Road plant into a secretive clean room, retooling assembly lines to electroplate thin nickel films onto steel. This breakthrough slashed nickel use by over 99%, making the barrier practical and affordable. But the process demanded near-sterile conditions. Plating baths ran around the clock, and technicians in full body suits watched for any trace of dust or humidity that could ruin a batch in minutes. Yet even with these precautions, the barrier's fragility became clear. In August 1944, a batch of newly installed sheets began to delaminate, peeling away under heat and pressure. Uranium hexafluoride seeped into the exposed pores, corroding the metal and threatening to halt the entire operation. The setback forced Chrysler's team to rapidly adjust the plating chemistry, tweaking phosphorus levels and extending electroplating cycles. Within weeks, production resumed, but the lesson was stark. A flaw invisible to the naked eye could jeopardize the whole cascade. Powering this operation required a dedicated Tennessee Valley Authority steam plant, with compressors pushing gas through pipes at hundreds of pounds per square inch. Every weld and gasket had to be flawless. Maintenance crews drilled to replace barrier modules in a single day. By war's end, K-25 delivered enriched uranium at a scale once thought impossible. Today, only the K-137 hatch remains, a heavy steel door that once sealed the barrier floor. It stands as a silent witness to an era when the fate of the bomb rested on a nickel-plated membrane, hidden inside the world's largest factory. Rows of steel columns, each standing 30 feet tall, towered over the S-50 site at Oak Ridge. The plant's 2,500 vertical diffusion columns formed a forest of stainless steel, each engineered to create an intense heat gradient, 1,200 degrees Fahrenheit on the hot side, 300 degrees Fahrenheit on the cold side. Inside these columns, uranium hexafluoride gas moved in a slow, controlled spiral, nudged by the difference in temperature. The lighter uranium-235 molecules drifted toward the center, while the heavier uranium-238 hugged the walls. It was a subtle effect, but multiplied across thousands of columns. The result was a steady trickle of slightly enriched uranium, a tactical boost that made the next stages of enrichment more efficient. Thermal diffusion was not a headline technology. Its yield was modest, raising the concentration of uranium-235 by only a fraction of a percent. But the S50 plant's value lay in speed and scale. By feeding its output into other enrichment plants, it gave the entire Manhattan Project a critical edge, shaving weeks off the bomb's production timeline. At full capacity, S50 delivered a product stream of 1.2% uranium-235, enough to raise the efficiency of gaseous diffusion by roughly 15%. In a war measured in months, that margin mattered. The engineering challenges were relentless. Each column had to maintain its temperature gradient without warping or cracking under thermal stress. Early attempts to bring the plant online too quickly led to a rash of failures. Columns split open, leaking corrosive gas and halting production. The solution was a slow, 12-hour ramp-up, allowing the metal to expand and the gradient to settle without sudden shocks. Operators, many cross-trained from other Oak Ridge jobs, learned to monitor the warm-up cycle with the precision of a laboratory technician, logging temperatures and flow rates through long shifts. They worked under strict secrecy, with little sense of the stakes or the impact of their labor. The S50 plant was never intended to stand alone. Its entire purpose was to act as a force multiplier, feeding slightly enriched uranium into the larger, more complex plants nearby. In the end, this tactical add-on, overlooked in most accounts, helped ensure that enough bomb material would be ready when the call came. The columns themselves have vanished, dismantled after the war, and melted down for scrap. Their contribution remains hidden in the shadow of more famous machines, but critical to the outcome all the same. On the banks of the Columbia River, the Hanford site took the Manhattan Project's ambitions to a new scale. Here, the challenge was not separating uranium, but making plutonium, an element that barely existed outside the laboratory. The method was as bold as it was untested. Bombard uranium fuel with neutrons inside a graphite-moderated reactor, then extract the new element from the spent fuel using chemistry never attempted on an industrial scale. The B reactor, first in line, demanded a constant flow of water, about 1 billion gallons each day, drawn straight from the Columbia. Intake tunnels, reinforced with concrete and steel screens, channeled the river's power through the heart of the reactor. Water rushed through thousands of aluminum tubes holding uranium slugs, carrying away the heat of fission before returning to the river. The graphite moderator, weighing 1,200 tons, kept the chain reaction steady, while operators monitored every gauge and valve for signs of trouble. In December 1944, a single fuel slug ruptured during removal. A crack in the aluminum cladding let molten uranium and radioactive gases escape into the cooling water. Within seconds, pressure surged through the system, forcing contaminated water into the intake tunnels. Emergency crews shut isolation valves in under half a minute, but not before hundreds of gallons had spilled. The breach exposed workers to intense radiation. Dose rates spiked to 500 Roentgens per hour near the rupture point. The incident forced a complete review of fuel fabrication and handling. From then on, every slug was inspected ultrasonically before removal, and new soft lift protocols reduced the risk of another rupture. Once the fuel had cooled, it traveled by rail to the chemical canyons. There, the bismuth phosphate process dissolved the metal in nitric acid, separating plutonium from uranium and fission products. Each batch generated thousands of gallons of high-level waste, which was pumped into underground tanks, an engineering solution that traded immediate safety for long-term risk. Hanford's reactors and separation plants operated around the clock, tended by thousands of workers who rarely knew the full nature of their task. Their labor, shielded by secrecy and the roar of the river, transformed abstract nuclear theory into a physical stockpile of plutonium. The scale of Hanford's machinery, the billion-gallon water intakes, the graphite stacks, the chemical canyons, remains almost unimaginable even today. In the race to build the bomb, this was industry as weapon, and the river itself became part of the machine. Behind every towering machine and labyrinth of pipes stood a set of decisions shaped by urgency and doubt. In 1942, the Lewis Committee weighed the options. Electromagnetic separation offered immediate, if costly, results. Gaseous diffusion promised greater efficiency but was unproven at scale. Some advocated for a single, focused effort, but General Leslie Groves refused to gamble on just one path. He approved both the calutrons and the K-25 plant, ordering construction to proceed in parallel. Policy memos from this period reveal a blunt calculation. With no guarantee that any one method would deliver bomb material in time, the only safe course was to build everything at once. This strategy demanded vast resources and an army of workers, but it also meant that every major engineering firm, every labor battalion, and every supply chain would be pressed into service. The result was an industrial mobilization, as complex as the bomb itself. The machinery of the Manhattan Project depended on an army of operators, most of whom never learned what their hands were building. At Hanford, new hires entered a 12-week school where the curriculum covered everything from basic chemistry to the careful handling of unfamiliar metals. Lessons stressed routine, how to monitor gauges, how to follow a checklist, how to report a reading that drifted out of range. Weekly exams measured not only technical skill, but also the ability to follow instructions without question. Each worker's health was tracked with regular medical checks, but the reasons for such vigilance were never explained. The daily regimen became second nature. Clock in, suit up, run through the motions, and keep silent about the details. For many, the job was just a series of tasks, a rotation of simple actions. Turn a valve, record a number, wait for the next shift. The real story, and the purpose behind the machines, remained locked away behind layers of secrecy. Precision became the watchword across every workshop and construction site. Machinists at Alice Chalmers cut calutron extraction slits to just 0.025 inches, thinner than a matchstick, while vacuum technicians pushed pressures down to 5 × 10 to the -7 torr, a level rivaling the best laboratory standards. Shop foremen checked tolerances with micrometers, knowing that a fraction of an inch could mean the difference between success and scrap. Meanwhile, construction crews worked around the clock, assembling prefabricated steel frames under floodlights to meet impossible deadlines. At K-25, entire assembly lines were ripped from civilian factories and rebuilt for barrier production, turning auto plants into clean rooms. The nation's supply chain bent to the task. Copper was rerouted from telephone wires, nickel from coinage, and thousands of boxcars delivered components from coast to coast. Every bolt, gasket, and panel had to fit perfectly, because in these machines, even the smallest flaw could bring the whole enterprise to a halt. Corrosive chemistry and mechanical surprises haunted every shift. At K-25, a single drop of water in the system could turn uranium hexafluoride into hydrofluoric acid, eating through nickel-plated steel and threatening to unleash toxic gas. In the summer of 1944, A compressor at the heart of the cascade spun out of control. A stuck valve sent pressure soaring and rupturing a 10-ton uranium hexafluoride cylinder. Workers scrambled to contain the cloud, their faces stinging from hydrofluoric acid vapor as alarms echoed through the plant. Emergency engineers tore into the piping, installing new pressure relief valves and doubling nitrogen purge flows. Each fix had to be invented on the fly, often in the middle of the night, with lives and months of production on the line. The machines themselves became a test of nerve and ingenuity, forcing teams to adapt faster than the hazards could multiply. Decades after the last Calutron shut down and the K-25 cascade fell silent, the true cost of the machines began to surface. Not in blueprints, but in medical records and compensation claims. The National Institute for Occupational Safety and Health launched a sweeping project in 1999, poring over faded exposure logs and reconstructing radiation doses for workers who had spent years in the shadow of secrecy. Their findings laid the groundwork for the Energy Employees Occupational Illness Compensation Program Act, which has since approved more than 21,000 claims and paid out more than $1 billion to former Manhattan Project workers and their families. Yet behind these numbers lies a gap that cannot be closed. Thousands of operators and laborers left no employment records, their exposure untracked, their stories lost. As the government demolished the K-25 building and shredded engineering drawings under classified orders, the machines themselves vanished from the landscape, erased from memory even as the health effects lingered. What remains is a fragmented legacy, compensation for some, silence for many, and the slow recovery of a history once buried by both secrecy and demolition. Today, the vast machines and unknown operators who made the atomic bomb possible remain erased from monuments and textbooks, yet their legacy endures in every debate over nuclear risk, secrecy, and technological power. As new technologies emerge behind closed doors, the line between invention and consequence blurs. The hidden machinery of the past still shapes what we build and what we choose to forget. Share your thoughts below.